Hi, I'm Scott Hader. We're going to do some more modern algebra, and this time we're going to be talking about cyclic subgroups and generators. So, first thing we're going to talk about, just a quick review on subgroups, what it means. And it's got to be a subset of the group, and it's got to be closed under the operation. You know, the identity's got to be the same identity in the bigger group, and each element of the subset has to have an inverse. It's also in the subset. So that's just a review from the previous video, and I'm just putting this here to kind of rehash a little bit, but I'm not going to go through all the proofs and everything like that. So we're just going to move right along here. And so one implication of that definition is that if a subgroup contains A, then it contains all the multiples of A, right? Because after all, the group is closed. The subgroup is closed, because that's part of the definition of the subgroup. So if it's closed, then A star A also has to be in the subgroup, and A star A also has to be in the subgroup, and so forth, right? So it contains all the, we can say, multiples of A. And, well, I kind of already told you why. But this is exactly what we're going to be talking about today with cyclic subgroups. We're going to be talking about actually the group generated by A and A star A and A star A and so forth. So you'll understand that more in just a minute, I hope. So go with me here. Now, for Z is a subgroup of Z. This is how we're going to write subgroup. It's a less than sign. So this is the multiples of 4 in the integers is a subgroup of the integers under addition. So we're going to be talking about addition today. It's implied that it's addition, so I'm not going to mention it every time. But if you're wondering what the operation is, it's addition. I'm just not going to specify it. So okay, so Z12, we're talking mod 12. What are the possible values? Well, it's 0 through 11, right? I hope you have some experience working with, you know, congruence classes. And but if you don't, it's basically just all the remainders when you divide the number by 12. 0 through 11, right? So 0, 3, 6, and 9 is a subgroup of Z12. If you add any of these two numbers together, you get another number in the group, and if you they all have inverses, additive inverses. 6 is itself, 3 is 9, and so forth. 0 is the additive identity, and so it's a subgroup. I'm not going to go through all the formal steps again because we got bigger fish to fry. But just to give you an example of what's not a subgroup, for instance, 0, 3, and 6. That's a subset of Z12, but it's not a subgroup. Because if you add 3 and 6 together, you get 9, which is not in our subset. So it's not closed, is it? Also, 4 and 8 is not a subgroup. Because when you add 4 and 8 together, you get 0, which is not in our subgroup. So there's no identity, and it's not closed as well. So just to give you a small example, sometimes we don't give enough examples of what's not whatever we're trying to show, and that can kind of, I think that can make the point a little clearer. So let's continue here, just giving you some basics a little bit to work with before we get started. So 0, 3, 6, 9, that is a subset, but it's also a subgroup of Z12, and we show that by, again, the less than sign. Alright, so is it a cyclic subgroup? So I know you're dying to know what a cyclic subgroup is, all this build-up, right? Don't hide it. Are you ready? So here it is, cyclic subgroups. It's exactly this set that I was alluding to earlier. We're going to call it H, and actually all subgroups usually we call H, because it comes after G, which is what we call groups. And it's the set generated by the multiples of A. All the multiples of A. So, which is the following set. And a to the 0 is just e. It's our identity. Okay, so you can see it's generated by a, isn't it? So since a is a generator, we're going to use the brackets, I don't know what those symbols are called, greater than, less than signs surrounding a. And so that's the notation we're going to show for being a generator. So example, the generator 3 is 3 to the 0, 3 to the 1st, 3 to the 2nd, 3 to the 3rd, and so forth, which is 0, 3, 3 plus 3, 3 plus 3 plus 3, which is 0, 3, 6, and 9. So when we have the exponent here, remember we're talking about addition. So 3, 0, that means 0 threes. 3, 1, that means 1 3. 3 to the 2nd, that means 2 3s added together. 3 to the 3rd means 3 3s added together, and so forth. So it's a little bit different than what you're normally used to seeing exponents, but I don't think it's a big deal to get used to. Moving on here, got some examples. So find the number of generators of a cyclic group having the given order. 8 and 60. So 8, if it has the order 8, we're talking about it's going to look like the group Z8, which is the set 1 through 7 in the integers, and 60 is the set 0 through 59 in the integers. So we got to find the number of generators for Z8 to start. So for 8, we're going to start out with 0, which generates the subset 0, or the subgroup 0. 1, you can see, generates 1, 2, 3, all the way to 7, and then 0. So if you put that in order, you can see that it actually is Z8. So 1 is a generator for Z8. Let's look at 2. 2, 4, 6, and 0. So you can see that it doesn't generate Z8 because there's missing numbers. It only has the evens of Z8. 3, 3, 6. The next one's 9, which is 1 mod 8. 4, 7. The next one's 10, which is 2 mod 8. Then 5, and then finally 8, which is 0 mod 8. And you put those in order, and you see that actually it's Z8. So 3 is a generator for Z8. So far we've found 2 generators for Z8. 4 is just 0 and 4. That's obviously not Z8. 5, I'll let you check it yourself, but I'll just tell you right now, it works. And 6, it turns out to be 0, 2, 4, and 6 when you put them in order. 7 is Z8. Okay, so do you notice a pattern on the groups that generate Z8 and the groups that don't generate Z8? 1, 3, 5, and 7, but 0, 2, 4, and 6 don't. It's all the numbers relatively prime to 8. Those all generate your group, your whole group. Okay? So that's really important to know. So 7, 5, 3, and 1, obviously those are all relatively prime to 8. It's not just the odds. In this case it's the odds, but it's not. Okay, so let's look at 60. And the generators, I just listed them out here. I'm not going to go through all of them, there's too many, but 1, 7, 11, those are the first 3, and the last 2 are 53 and 59. I counted all of them up, I got 14. So you might want to do the same. Basically, you're just finding the numbers relatively prime to 60, which makes a lot of sense. And we'll just go ahead and I hope this only takes a minute, but I don't want to take too much time, but it makes sense why they're all relatively prime. For instance, talking about Z8, going back to Z8, let's go back for just a second. 5, for instance, generates Z8. Well, what's the lowest common multiple of 5 and 8? It's 40, right? And you have to multiply 5 by 8 to get to 40. So there's going to be 8 elements that you're going to have before you ever get to 0. So I hope that kind of makes some sense on why it's the numbers that are relatively prime to 8. Alright. So, next problem is find the cyclic subgroup of Z30 generated by 25. So what's that mean? We start with 25, we add it again, we get 50, add it again, we get 25, and so forth. And you mod those by 30, it turns out to be 25, 20, 15, 10, 5, and 0, which when you put it in order, 0, 5, 10, 15, 20, and 25. So that's our subgroup, generated by 25, and we're talking mod 30. You could also generate this cyclic subgroup, the same subgroup, 0, 5, 10, 15, and 20, and 25, if you use the generator 5. But those are the only two that generate this specific cyclic subgroup, 0, 5, 10, 15, 20, and 25. Okay. So, what's the difference between a cyclic subgroup and an ordinary group? Take the rational numbers under addition. It's a group, right? It's obviously a group, but there's no rational number that generates all the rational numbers. Okay? For instance, like try 1. Well, if you add another one, you get 2. You're missing all those fractions between 1 and 2. However, the integers with addition, you can generate those with 1. You add and subtract 1 enough times, and you're going to get every integer. So, the integers under addition is a cyclic group, and the rationals under addition is just a group. Okay, so in fact, by the way, that's the only infinite cyclic group. It's got to be isomorphic to the integers under addition. It's kind of interesting. Only one case of the infinite cyclic group. Okay, so now we got another problem. Find all the subgroups of the group Z36 and all the cyclic subgroups, obviously, and draw a lattice diagram for those subgroups. So we start out with 1, and that's Z36, that's going to be the whole group. 2, it's going to be all the evens. The cyclic subgroup generated by 3, 0, 3, 6, all the multiples of 3. 4, the multiples of 4, between 0 and 36. 6. Now, we skipped 5. Why do you think we skipped 5? We skipped 5 because 5 is relatively prime to 36. So it's going to generate the whole group. So it's going to be the same as the cyclic subgroup generated by 1. It's going to be the whole group. So we don't need to show that again. And in fact, you only need to show what the subgroups are, what the cyclic subgroups are, for numbers that go evenly into whatever this is. So for instance, for 36, we only need to show the numbers 1, 2, 3, 4, 6, 9, 12, and 18. Those are the only numbers 0 to 36 that go evenly. All the others are just going to be repeats. So that's a good trick to know. So 9 is 0, 9, 18, 27. 12, 0, 12, 24. 18 is going to be just 0 and 18. And what's the last one? Do you know? It's just 0. You can't forget that one. It is a subgroup. And it's the trivial subgroup, trivial cyclic subgroup. So you don't want to forget that. So in all, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 here. And let's show the lattice diagram. So this is what a lattice diagram looks like. And so we have the whole group on top. And you see that 2 and 3 are both contained within the whole group, obviously. 2 being the evens and 3 being the multiples of 3. And then you see that 6 here is contained within 2 and 3. So it's a subset of both 2 and 3. However, 4 over here is only a subset of 2. And 9 is only a subset of 3. 18 you can get by either 6 or 9. It's contained within both of them. 12 is contained within 4 and 6. The cyclic subgroups generated by 4 and 6. And 0 is contained within all of them. So, but just to point out one thing, it's not like 12 is only contained within 6. Obviously it's contained within 2 as well, and the whole group as well. This just shows just sort of the hierarchy from largest to small. So I hope that makes intuitive sense sort of for you. Okay. So one cool property about cyclic subgroups, I think it's cool anyway, is that each one is a abelian. And remember what abelian means. Abelian is commutative, right? So let's prove it. Let G be a cyclic group, and A is a generator of G. So that G is the group generated by A, which is A to the n for all n in the integers. So we start out, we have 2 elements in our group, and we can rewrite those two elements as A to some power, because our group is made up entirely of elements that are A to some power. Okay, so we're going to make sure those are different. So we picked R and S. So G1, G2 is going to sub in AR and AS. Choosing your rules, you can add the exponents, combine it, and then addition is commutative, always. Always, always. So we can just flip those and break those back up, and look, we end up with G2, G1. So G1, G2 is G2, G1, which means it's commutative. Thus, every cyclic group is abelian. So that's a really good thing to know that comes up again and again. So we get a check mark, bringing back the check mark. Okay, another example here. Find the orders of the subgroups of Z6. So first we got to find the subgroups of Z6. So 1, the subgroup generated by 1 is obviously the whole group, which is 6 elements, right? 0 to 5. Subgroup generated by 2 is 0, 2, and 4, which there's 3 elements. And by the way, these bars on the side, this looks like absolute value. That means order in modern algebra. So just remember that notation. And then our third subgroup is the group generated by 3. And that turns out to be just 0 and 3, which there's 2 elements. So the order is 2. And final one is subgroup generated, the trivial cyclic subgroup, which is just 0, which is just 1. 0 is just 1 element. Okay, why didn't we use 4? Why didn't we find the cyclic subgroup generated by 4? Because it turns out to be the same cyclic subgroup generated by 2. And 5 is the same cyclic subgroup generated by 1. So we don't need to show repeats. Remember, just the numbers that go evenly into this number. Okay, here's a theory question, fun little question. P and Q are primes. How many generators generate the cyclic subgroup Z of PQ? It's kind of a cool question. And so Z of PQ, so basically we're trying to find all the numbers relatively prime to PQ. Alright, so we've got to take out some numbers. We've got to start with PQ, and we've got to subtract all the multiples of P, we've got to subtract all the multiples of Q, and we've got to subtract PQ, obviously, because PQ is not relatively prime to PQ. Okay, and the multiples of P turn out to be just Q minus 1, and if you don't believe me, you can just write out an example. Like, you can even make the numbers real small, like P is 2 and Q is 5. The multiples of 2 turn out to be 5 minus 1, which is 4. There are 4 multiples of 2 mod 10. Okay, and so what we got is PQ. We're going to minus Q minus 1, and we're going to minus P minus 1, and we're going to subtract out PQ, which is 1. And it's kind of cool when you do a little factor by grouping, you end up with Q minus 1 times P minus 1. So that's kind of works out kind of cool, I think. So that's that one. And another very cool one, I think. I really like this one. It took me a long time to kind of wrap my mind around it, but after I did, it kind of the light bulb went on, and I thought it was very interesting afterwards. All right. So here we go. Let G be a group, and we got A in the group, and this element A generates the cyclic subgroup, a cyclic subgroup of order 2, and it is the unique such element. Show that AX equals XA for all X in G. So X is any element in G, but A generates a cyclic subgroup of order 2, and it's the only element. It's the unique such element. So it's the only element that when you square it, you get the identity besides the identity itself. So this one you might have to review just a couple times, but I promise you it's worth it. Once you understand it, it's a very interesting problem. Once you kind of wrap your mind around the whole thing, it's very cool. So it gives us a hint to consider XA X inverse squared. It's kind of a vague hint, but let's talk about how we can make use of it. So things to note. There's only one element, A, that generates a cyclic subgroup of order 2. That's very important. Another thing is that order 2 means the set, that cyclic subgroup, it looks like E and A. There's only 2 elements in it. And of course, one has to be the identity, so the other one's just A. Another thing is that A squared is E. Obviously. So let's get started on this one. And so I'm going to give you a little idea of where I'm going with this. We're going to end up with XA X inverse. We're going to show that is A. And after you multiply on the right by X, you end up with XA equals AX, which is what we're ultimately trying to show. So our whole point is to show that XA X inverse is A. We're going to start by showing that it's not E. If XA X inverse were E, when you multiply on the right by X, you end up with XA equals X, which means that A must equal E. And A is not E. So XA X inverse is not E, and now when we square XA X inverse, that means we multiply them out side by side, and X inverse times X in the middle, that's just E, so that just goes away, and then we end up with XA times A x inverse, and that's, again, multiplying them out. A times A is A squared, and remember, we stated earlier that A squared is E, and so all that turns out to be just E. So far we've shown that x inverse is not E, and we've shown that, but when you square it, you get E. So if you square that element and you get E, and since it's not E itself, it is A, since A is the only element of order 2. It's the only element that when you square it, you get E, besides E itself. So, once again, this one might take a little while to go back and forth just a little bit to wrap your mind around it, but I promise you it's worth it. It's a very interesting one once you get the whole picture. So we've shown that XA, X inverse, it has to be A. And since that's true, multiply on the right by X and piece of cake after that. Got a little QED there. Changing it up from the check mark. And that's all the material I have for this video. So, thank you very much for watching. I hope you liked it. Please comment, question, etc. And have a nice day.